Pretty cool. An advanced EEG signal simulator. Basically, it's a tool that lets you play around with brainwaves, understand different mental states, and see how real-world noise messes things up, giving you a shortcut to understanding this complex data.
Exactly. And it's more than just a visualization tool. Think of it as a controlled sandbox for brain signals. So EEG itself, electroencephalography, that's the non-invasive way we record the brain's electrical buzz, the brain waves from neurons firing together.
Right.
What's really key here is the simulator makes a synthetic EEG signal. It's artificial, but it mimics real brain activity. It does this by combining the basic brain waves, delta, theta, alpha, beta, and you can add noise too.
Okay.
And that's incredibly useful for learning, definitely, but also for things like developing algorithms, maybe for brain-computer interfaces, BCIs, because you have this clean, predictable signal you can control.
Got it. So let's unpack how this simulator is actually laid out. It seems pretty intuitive. You've got controls on one side, and then the visualizations, the results on the other.
That's right. The controls are where you shape the signal. You've got brain state presets first. These are shortcuts. Click relaxed meditative, for instance, and boom, you see strong alpha waves pop up in the spectrum.
Ah, instant feedback.
Exactly. You visually confirm the signature of that state. It helps train your eye, which honestly usually takes a lot longer looking at raw data.
I could see that being super valuable. And it's not just ideal states, right? You mentioned artifacts. There's an artifact simulation section. Why is adding the messy stuff important?
Oh, it's absolutely crucial. Real EEG is never clean. You always get signals that aren't from the brain. So here you can add things like muscle artifacts, EMG, that high frequency noise when you maybe clutch your jaw.
Okay.
Or eye blink artifacts, EOG. Those are those big, slow spikes you see when someone blinks. Adding these is just about seeing noise. It's about understanding how much it can contaminate your data.
Right. So you need to know how to deal with it.
Precisely. It shows why cleaning the data, artifact rejection, is often the very first critical step in any serious EEG analysis. Simulating helps you build and test methods to do that effectively.
Okay, it makes sense. So if I were building a BCI, I could train my algorithm to spot and maybe remove these artifacts from the get-go. Beyond presets and artifacts, you can also fine-tune waves, right? Get more specific.
Yes, definitely. There are simple sliders to just crank up or down the amplitude, the power of each main wave. Delta, theta, alpha, beta, or you can go into what's called customized mode.
And that lets you?
That lets you precisely set the center frequency, the bandwidth, and the amplitude for each of those wave bands individually. So really granular control.
And what about those dotted lines on the spectrum graph, the spectrum overlays?
Good question. Those are like ideal Gaussian curves. Think of them as theoretical benchmarks, like perfect, smooth bell curves showing what each pure brainwave would look like if it were completely isolated. They give you a reference point.
Okay, so you set everything up with the controls. Then you look to the right at the visualizations. The top one is the power spectrum. That's the frequency view.
Correct. It's showing you the output of a fast Fourier transform, an FFT. Basically, it takes that wiggly line over time and breaks it down, showing how much power, how much energy is at each specific frequency. You'll see peaks where you're...
Okay, so one question is why it's hard to visualize EEG data, time series data in the time domain graph. Also, it's not quite obvious when we changing, for example, the bandwidth of the theta wave. The change on the simulated EEG waveform in the time domain is not obvious. Can you explain that? Let's pop it into the next chat because it's a big topic. Just continue listening to this one.
So that's how you see, lots of alpha, or, okay, theta is strong here.
Exactly. It's your window into the brain's main rhythms. Below that is the simulated EEG waveform. That's the time view, the raw voltage signal, second by second, showing the sum of all the waves and artifacts you've mixed together over a 5-second window. That's what raw EEG looks like.
Got it. Now, you mentioned something interesting earlier, a potential aha moment. Sometimes the actual signal spectrum, the filled blue area, doesn't perfectly match those dotted ideal overlays. Why is that? It's not a mistake.
No, definitely not above. And it's a really important concept. Think about it like mixing ingredients. The blue spectrum is the final cocktail, the result of mixing delta, theta, alpha, beta, maybe some noise. Altogether, the dotted overlays are like looking at each pure ingredient separately. When waves mix, they interfere. Sometimes their peaks line up and add together. That's constructive interference. Sometimes a peak meets a trough and they partially cancel out, destructive interference. This constant interaction means the combined signal, the cocktail, has a more complex, sometimes kind of lumpy spectrum than any single perfect ingredient would have on its own.
Ah, I see. So the overlays show the theoretical input, but the blue shows the messy interactive output, the reality of the mix.
Precisely. The overlays guide you, they show you what's contributing, but the blue area is the more realistic combined result you'd actually measure.
That cocktail analogy really helps visualize it. Okay, so this simulator is already powerful, but thinking ahead, what's next for tools like this?
Oh, there's lots of potential. You could imagine adding gamma waves linked to higher processing, more artifact types like EKG from the heart, or maybe that 50 or 60 hertz hum from power lines.
Yeah.
You could have more advanced analysis like spectrograms showing how the frequencies change over time, or even simulate multiple EEG channels at once to look at brain connectivity, maybe even import real-time data to compare side by side. Lots of exciting directions.
It really feels like a powerful learning and development platform.
It really is. Ultimately, this kind of simulator helps demystify EEG. It makes these complex signals interactive, letting you build intuition by playing with the components, the waves, the artifact. That foundational understanding is just invaluable, whether you're in neuroscience, biosignal processing, or trying to build the next generation of BCIs.
So it lets you get hands-on with the theory, thinking about that interference, that cocktail effect we discussed. How might understanding those nuances shape future tech? Maybe how we build BCIs that are more robust to real-world brain activity, or even how we interpret signals related to neurological conditions. What insights might you find by exploring this simulated brain landscape?
So we added the prompt, the question into Notebook LM. It found like 10 additional sources. One of them is still trying to access. In Notebook LM, you have to delete the current audio to generate the new one, which is a bit odd. Delete. It's not getting deleted. Okay. Yeah, it's generating. So we wait for the podcasters, the professional podcasters to set up again. I don't know what they're doing. Yeah, robots writing script, preparing for the podcast session. Yeah, while a Notebook LM is getting ready. Yeah, if you have any questions about the website, go for it. We're also gonna be doing development during this session as well. So for development, currently, I'm tool agnostic and don't care for, people keep asking what's the stack, what are you using? We'll be using anything that we can publish, essentially. So anything that is shareable. Anything that is shareable. Yeah, I'm doing a lot of this like ultrasound and X-ray visualizations. Yeah, we have PPG SNR, so signal to noise ratio. I also have PPG another signal to noise ratio for PPG. So we split, essentially had to do simulations out of this one. This one's based on a paper. I won't read the title, it's boring as. Sorry. But essentially it's showing the differences between recording. So PPG is what's being recorded in your smartwatches. And this paper shows that there's a difference in recordings depending on if you stand, sit, lie down. There's also when you stand, so there's a difference depending on how. So if I put my arm up here, do I record PPG anymore? No, I'm not going for a run. I don't know how to do it. I forgot. No. There you go. So 95%. Yeah, I don't know. It does it like every 4. It says, I have to keep still. Yeah, that will be a problem. maybe that's maybe that's why the last measurement that was made was like 4 days ago. Yeah, you can't do it because I'm not still enough or something. So it was 95% oxygen saturation. Can do content on that as well. Still measuring. Yeah, 95%. It's always showing 95%. Yeah, that PPG measurement is quite weird that way, because yeah, it always varies between whatever 95 to 99%. So there is the dynamic range is pretty low, I would imagine. So I don't know how this device is doing it, or how accurate they're doing it. They're just toys. Notice this big YouTube channel that compares all these smartwatches and things. So he's benchmarking them to the chest strap, which is a toy by itself. So what's the point? I don't know. Yeah, he never compares it to like medical grade devices. So it's a bit of a misnomer there. Different morphologies. So you have like lambda waves are positive sharp. Lambda? Do we have lambda? No, we don't. It's high frequencies. Do we need to add lambda? I don't know.